Okay. Morning. So today we want to talk about slightly different topic, machine learning security. And on the next lecture, we're going to talk about the privacy aspects of the machine learning. So it's kind of like, we talked about the story that we tell you so far is, we start with, basics of the security. We talked about, cryptography as well, right? And if you remember early on, I talked about, computing system as this, pipeline of different things, right? We said that we start with like, sensors that, get the physical activities and then send this digitized information into some sort of a local processing system, right? This is basically where our computer is, and the majority of the attacks can happen at this point. And then all of this, we kind of can have two different paths. We can either, go directly to the actuator and actually do something. So our loop is kind of closed between sensing something from the physical environment and then doing some actuation to the physical environment. Alternatively, we can go through the network, right? And go to some, backend cloud processing system. And again, this way, this is another computer that, you can attack in multiple different ways. And usually what happens is that this information goes back into the local system. And again, the local system do some actuation in order to have some impacts into the physical world, right? So, and we said that generally any system that we kind of would deal with would be an instance of this in real world. Your laptop basically is a mini version of a sensor computation. And usually it doesn't really have an actuation. It doesn't have a physical actuation, but usually what it does is basically your actuator, in this case, would be your kind of like a display or communication with the outside world through the network, right? So this would be the story of your laptop, basically. But there is no difference between your laptop and any other device. Generally, all of them has the same issue. And then we talked about things that the attacker can do, right? So we first talked about what would happen if the adversary actually do infiltrate into your system and actually start doing something malicious. We talked about different options of malicious activity. We talked about different malwares, having the actual, impact on the system through running some payload, including ransomware, worms, etc., etc. Then we kind of like take a step back and talk about, okay, how the attacker can actually infiltrate the system, and we talked about memory safety and security. And now we want to talk about one of the systems that's generally looking at the whole system and saying that, okay, now that we have these different, powerful tools in terms of an attacker, okay, how we actually can attack an actual system. And the system that we're gonna focus on and we're gonna analyze is a machine learning system, all right? So the biggest question is, why is it important for an adversary to attack a machine learning system? And generally, what should we care about? Why should we care about machine learning specifically? And why did I pick machine learning? So the answer to this question is basically, most of you already know that, machine learning is being used in almost every system these days, right? So it's because of its unique, abilities compared to conventional computing, machine learning is becoming more and more popular, specifically when we are dealing with, large set of data, input data, and sensors. So just naturally, it's a really good way of computing things on an edge cloud setting, okay? And it's growing more and more. You use it in many different systems, especially, more future and emerging applications such as, autonomous systems, robotic systems, all these IoT devices, etc., etc. So there is definitely is a growing, use case for machine learning, and that's why it's kind of like interesting to know and learn about the threats to a machine learning system as a whole. Okay. But of course, I'm not sure how many of you actually do know about machine learning or have taken any course on machine learning. Just raise your hand if you already taken any course in machine learning. Right, kind of have a little bit more than that. Okay. So before actually jumping into what the machine learning, security issue is, I think it's important for us to actually learn a little bit more about machine learning. I'm going to, quickly go through it. Let me know if there's any part that you don't understand fully, and then we can go back and learn about it. And of course, you can always, take some time and read some additional materials. So some of you already know all of these things, so it just would be a quick review. For those of you who don't know, that would be just a 10,000-foot view of what is machine learning. So generally, there are three types of learning that AI or artificial intelligence machine learning can be used. There is supervised learning, there is unsupervised learning, and there is reinforcement learning. What we are mainly focused on when we are talking about attacks, we are mainly talking about supervised learning. So supervised learning is basically this problem of learning some sort of characteristics of the data and trying to map some inputs domain. Let's see. Some input domain to some output domain. And basically supervised learning is kind of like help you with that. Usually with supervised learning, what you have is labeled data, so you know what's your input and output is. So for a given input, what is your given output, or what is your label? And what you're trying to learn is by seeing a bunch of these, pair of X and Y's, you kind of learn what is the relationship between X and Y. So the next time that you see a new X, you will be able to detect what is Y, right? So this is basically very, very simple definition of what is supervised learning. Yeah.
Is this without the knowledge of like the function that maps X?
Yeah, if we knew the function, then the problem is solved already, right? The problem is we don't know exactly what is the relationship between X and Y. If we know it, then the problem is already solved, right? So for example, we can probably guess it, but sometimes there's just no known function that. So for example, think about something like image classification. You have a bunch of images. And let's say you want to say whether this is male or female, like gender classification. And in order to understand that, there's no known function that, oh, this is an image. These are the, bunch of mathematical operation that you can do in order to get the final output. So machine learning naturally fits into this class of problems because it just say, okay, this image male, this image female, this image female, and so on and so forth. And then train some sort of a model in order to predict this. And of course, when you're doing this, there's always some notion of error with the system, right? So we're never actually doing a full answer, but we try to get to that, final answer. So that's the story of its supervised learning. We're actually going to talk more about supervised learning. There's other two classes of, learning as well, which is unsupervised and reinforcement. So unsupervised is basically when you're talking about some characteristics of the system, not necessarily mapping. So for example, clustering is the biggest, one of the biggest use cases of unsupervised learning. So let's say you have, a bunch of different data that kind of scattered around your field. What you want to learn is kind of like, just draw some characteristics of the system and trying to maybe categorize this, maybe, group this together and so on and so forth. And you don't know beforehand what is the feature, what is the characteristics that you want to use, but you let the machine learning to learn this and tries to, categorize this for you. And then there are lots of use cases for this that we don't necessarily talk about, but you can probably see that what are the use cases. So that's the story of unsupervised learning. And finally, there is another group or type of learning that's also very important, and that's reinforcement learning. So the story of reinforcement learning is basically learning what to do based off some rewards and some actions. Okay, so basically you have an agent or a machine that, let's say, just make some arbitrary decisions. And based on this decisions, you see, so you want to, for example, this machine or this model to learn something. For example, learn how to walk, or learn how to drive, or learn how to play a game, etc., etc. So of course, you don't know what is the best strategy to do that. So what you would do is that let the machine just do some arbitrary things, like move the arm in this direction, or play the game, play this specific piece of board to this specific part of the board, so on and so forth, depending on what the application is, and eventually measure the success rate of this activity, this action, and tell the machine that whether this action was successful or not. Because eventually, for example, the goal is winning the game, or the goal is walking, or the goal is running, or the goal is some specific action, right? If this specific part of the sub action leads to this final goal, then you have to report the system and tell the system, oh, this is a good way of doing this, right? And then you just do it iteratively until you actually achieve that goal, right? So it's kind of like a back and forth game between some sort of an agent and someone who kind of just evaluate these actions and tell the agent whether they are going into the right direction or they go into the wrong direction. And this way, you can learn how to do very complex things, including how to play like chess, or how to play AlphaGo or other things, or how to walk, or how to play tennis, etc., for a robot, and without actually knowing exactly what you're doing, right? So without actually having a specific algorithm to say, oh, check this and do this, and so on and so forth. And the reason for this that we don't actually follow specific heuristic is usually these are like NP-hard problems. So for example, for chess, you cannot brute force through all the possible actions, because that's too many. This takes forever for you to compute those. That's why you need to kind of like randomly pick some action, and based on that do that activity. Okay, so that's the story of reinforcement learning. Actually, all of these are really wide area of research and knowledge. Specifically, things like reinforcement learning these days become more and more popular because the class of actions that they can achieve is actually quite huge. For example, specifically for robotics, this is like a big area of research. So we're gonna particularly look at the supervised learning, and mainly because the attacks and the impact that the attacker can have is mostly on the supervised learning part, and we're going to discuss why. Any questions here? So to just focus a little bit more on what is supervised learning. Basically, supervised learning is using a model, and that model is kind of like some hypothesis, so we can decide what that model is. In order to learn some mapping between inputs and the target variable or target outputs, right? So as I said, we have a bunch of records, and then we already know the answer to these records. So that's usually what's called training data. And what we want to know is that we have some other records that we don't know the answer to, and hopefully, if our machine is modeled and trained well, we can just feed these records to this machine, and that can generate the outputs that we want, and hopefully these are correct outputs, right? So that's the story of supervised learning. So there are usually two classes of supervised learning: regression and classification. The difference between the two is that regression tries to give you an answer, usually in either integer domain or some continuous domain. So for example, let's say you want to estimate what is this function. So let's say you have something like this is your data distribution, this is your y, and this is your x. So these are your inputs and these are your outputs. And what you want to do is being able to find a model that accurately predict all the points in this. So for example, if you have a new point, let's say here, you don't know, obviously you don't know this exact distribution, so your hope is that you can actually accurately find fx, which hopefully will be somewhere near here, all right? So generally regression is like this problem of finding this input, this output value that is closest to some continuous distribution. The classification, on the other hand, is usually just labeling data from some discrete domain. So you have a bunch of different inputs. The inputs could be either continuous or discrete, but the outputs is only some classes, so some finite number of classes. Okay. So for example, in the gender classification, it's male or female. In age classification, is maybe a number between 0 to whatever 200 or 100. So it's usually we have some finite number of classes, and the goal of the machine is trying to classify this data, saying that which class this data belongs. Okay, so that's what we usually do for classification. And again, we kind of like to narrow down our focus. The problem of machine learning security is usually focused, as I said, on supervised and maybe focused on the classification output. Okay, and the reason, again, we're going to talk about why we are looking at this, but also it's important to mention that supervised classification is kind of like the most popular way of machine learning these days. So many of the problems that we are dealing with when we really need to is basically a classification problem in most cases. Not that others are not important. Of course, there are many other use cases for them, but classification problem using supervised learning is something that there are lots of different applications. All the image classification, natural language processing, and all those things usually falls into supervised classification. Any questions so far? All right. So now let's focus on the classification problem, which is subset of supervised learning. So as most of you already know, usually for classification problem, we have two phases. We have the training and we have the testing. Usually for the testing, we call it inference. So the idea is, as I said, we have a bunch of data and we have a bunch of different labels. And we already know this mapping. So we already call it label data. So what we need to do is get this and have a machine learning model. We're going to talk about what this model is. But think about it for now as a simple, like maybe a linear model, something like y is equal to theta 1, theta 2 times x, right? And so x is basically this, and y is this. And what we want to learn is these two variables, theta 1 and theta 2, right? And this is just maybe just a very simple linear approximation of this problem. This is actually more of a regression problem actually, but let's say that these are discrete values, okay? And then this way we can actually have a classification problem. And this way we kind of like the problem becomes, okay, how to learn these two specific variables, and then in order to learn this, we need to kind of iteratively go through our training data in order to learn this. Once we have that, and let's say we learn the systems good enough, now it's time for the testing or the inference. Now it's time to actually use this model for some unlabeled data. So the next time there is a new X coming into the system, and we use this model with these two values, and what we're going to do is that we're going to find this Y. Right? And this way we can just keep using this model to predict the outcome of the system based off this new axis. Right? Again, this could be regression or this could be classification, doesn't matter. In both cases, the model works like this. For classification, this y would be some discrete values. For regression, this y would be an actual continuous line. Does it make sense? So now the big question is, okay, how do we train the model? What is the model that we have to use? And how should we do the training? Like where this magic actually happens, right? So you basically need three things for the training. You obviously need your label data, which as I said, is some pairs between your inputs and outputs. And one thing to pay attention to is that usually the input is, it's not a single value, but it's generally a vector of different values. You typically call them features, so different things in order to make a decision. So let's say for your image classification problem, your features are basically pixels of your image. Because at the end of the day, an image is a 2D array of some values, some pixels, right? Some colors, like RGB values, etc., right? Or this could be, for example, for your loan application, in order to decide whether you should be qualified for getting a loan or not, there should be probably a list of features, including your income, your education, your history, etc., etc. And based off that, the outcome would be something like yes or no, whether you're qualifying or not. And any other classification problem that you can think of, there are some features, and based off those features, you make a decision, right? So those features is usually your name. The second thing is the actual model. What is the actual mathematical function that you want to use in order to predict the outcome, right? And this model is not something that this just magically happens, right? It's at the end of the day, it's just there is some mathematical representation for what your model is. So, for example, in the case that I told you, it could be a1 in 2 times x, or it could be any sort of polynomial functions, right? And this could be your model. Your model could be actually have some nonlinear activity in it. So maybe it could be something like a2x and f of that then results in y. And this f could be things like, tangent hyperbolic, could be another function that we usually called ReLU, which we're going to talk about. It could be anything else. It could be any nonlinear function. It could be any if and else. It could be anything that you want to use. Okay. So basically, your model would be that, and the goal is finding these parameters in your model, whether it's linear or nonlinear. There should be some parameters that is unknown to you when you haven't started training your system. And the goal is during the training, you want to find these parameters, right? So this is really the goal of the training. And we usually call these weights in our systems, right? So the goal of the training is finding this weights. And if you have this weights, basically means that the model is trained, right? We usually use W to show. Okay? And now that we kind of know what we're looking for, so we have the input data, we have the labels, we know the model, we know what we are looking for. Then the question is, okay, now that I have these pairs of x and y, how can I use this x and y's? And I have multiple of them actually. How can I use them in order to find this maybe alpha 1, alpha 2, alpha 3, and so on and so forth, such that we want to make the system as accurate as possible, right? So we need to find this way. So this is basically what we call the training algorithm, and that's what I'm going to talk about in the next lecture, in the next slide. Okay. So this is kind of like what we're looking for in a training system. Does that make sense? So the training algorithm is kind of like this back and forth iterative process where we essentially have a bunch of inputs. So for example, in this case is image of different car. And what we want to do is that we have the model. In this case, this is a neural network that I'm going to talk about, but just think about this as some function, mathematical function. And what we do is we put the image, we go through this f of x and we get our y. And then we're going to need to kind of what's called a back propagation to measure how much accurate this estimation was, and then try to fix the error, reducing the error of the system in order to reduce this error so that the next time we give this image to the system, we get a better result. So it's basically the path would be something like we go this way, we give the image the x goes here, this is the forward path. We get our y, we calculate the error with some loss function that I'm going to talk about. And then based on this error, we need to change this parameters inside this function. We call it back propagation or backward propagation. And then goes back to this x, and then we repeat this process with the next x, next x, next x, and so on. And we continue doing this until we have this error that is like smaller than some amount, some threshold. And that's where we're kind of saying that this model now represents this data probably pretty well. Question.
How does it know if it found an error or not?
So remember, when we are doing the training, we have both x and y, right? So remember, we have label data. So we already know the answer. Okay. So what we do is kind of testing our system to know how well it can predict that answer. So what we do is that we send this x, but we already know what should be the y, what should be the answer. So we get this y and compare it with the known y, and this way we kind of calculate the loss. We don't exactly like subtract them. There are some loss function that we can use, but generally the idea is how far is this prediction is from the actual prediction.
And one more question about the previous slide. Where do we use the weights, or what are the weights used for again?
So again, this function is, so this machine learning function is nothing but an actual mathematical function, okay? What that mathematical function is really depends on what type of classifier are you using. Are you using, for example, a neural net or an SVM or logistic regression, etc., etc. We can go and talk about that. But just generally think about this function as some linear combination of some variables and the inputs, okay? And maybe at some point some nonlinear activities as well. So you maybe like you have polynomial functions that just multiply things together, add them together, and maybe you also apply some nonlinear function to some if and else function. Okay. And what you want to know is that, okay, what are these parameters? What are these weights that I need to multiply my input and add my input to, so that I can kind of have the best estimation possible of what.
So the weights are the circuits here.
Yes, kind of. Yeah. Once we talk about the neural, so this is a neural network basically. Once we talk about the neural network, you'll see exactly what is the mathematical function. But for now, think about a simple linear like a plus bx, something like that. So in this case, our weights are a and okay. Any other questions? And once we have that, we're basically done with our training. Now our inference basically becomes just sending some inputs. We only this time have the forward progress, right? And we get our label, and hopefully this label is right. Okay. So that's kind of like the model training. So for training, there are three different things that we need to know. First of all, there is no exact solution, or there is no closed form solution, as I just described, right? So if we have x and y, and if we know exactly what is the relationship between x and y, of course we can train the system to find that f, and this way we get the perfect accuracy. The problem is that we usually don't know what that is. So we usually just focus on what's called an estimation of f. Okay. So we kind of think that, okay, f, the actual f is some function that we don't know, but what we can find is this f prime, which hopefully is very close to f, at least in most points, right? So the training algorithm, what it does is basically creating some estimation about your system, not exactly finding the exact closed form solution, okay? So we're not solving a system of equations of x and y's to solve this problem, because generally we don't know what is the relationship between x and y. So that's one thing to know. The second thing is, in order to do the training, we need to kind of like find this objective function and calculate this error. There are multiple ways of calculating the loss. It could be as simple as just measuring the Euclidean distance between the label and the prediction. But usually we use things like, second order norm, third order norm, and so on and so forth. Or mean square errors, MSE. There are various ways of predicting and, calculating the loss. And the reason that we are using this different method is basically kind of balancing between the largeness of error versus the smallness of error. So you want to, this true choice of the loss would be very important to find the best distribution and the best, variables for your system. It's a long story about like how do we pick the loss, but probably if you guys have taken, stat classes, you have dealt with this generally a lot. Okay? So generally the idea is that finding some function to calculate the loss between the input, between your prediction and the actual labels. And finally, what we do and what's been, what very widely used is in order to do this iterative process of selecting an input, putting it into the forward progress, and then putting it backward. We usually use this iterative algorithm called gradient descent, where the idea is that if you want to find a minimum points or the maximum points in your system, what you can do is basically start randomly from somewhere, let's say from here, and then you kind of calculate the gradient of changes in order to actually get closer and closer to where the gradient is basically equal to 0. And that point would be where your minimum function is, right? So if you think about this as the loss function, what you want to do is minimizing your loss, obviously, right? So what you can do is that going to the direction of minimizing the loss. If you can find the minimum of your loss, then you basically your model is trained perfectly. And in order to find that loss, you need an algorithm to go to the right direction, right? And this way we usually use this iterative process called gradient descent. There are some details about gradient descent that we won't talk about, but probably most of you already know what it is. But generally, the idea is that if this is your loss function, what you want to do is that no matter where you start, right? So if you start here or here or here or even here, if you actually go into the right direction, which is the descent order, where the loss is actually reduced, then you can actually find this minimum point. And this minimum point is where you want to be because that's the minimum amount of loss that you have. Of course, problem may not be as simple as this. You might have scenarios like this, where you have what is called a local minimum, and you have something like a global minimum, or you have some areas that are flat, right? And depending on where you start, you can actually might have run into different scenarios. So for example, if you start here with your gradient descent, you're going to go here, and you're going to kind of stuck at this point because based on the gradient descent algorithm, if you go into this direction, you see that your loss is actually increasing. So you only stay here forever. And unfortunately, you kind of stuck in your local minimum, right? What you want to do is ideally finding this point. So if you're here, you might actually be able to go up the hill and then go down from there and then actually find this point. Or the chances that you actually stuck in this is also pretty good. If you are somewhere, let's say, something like this as well. If you start somewhere here with gradient descent, you're going to go here. But then you're going to get into this flat point that no matter which direction you go, nothing really change. And in that case, your algorithm might also just settle for some point here and then stop. Okay? And this is also another problem with the gradient descent. So what we usually do is what's called stochastics, or adding some randomness to this, where essentially instead of always starting at a specific point, we start at multiple different points or repeat this experiment multiple times so that we kind of guarantee that we are finding this point here. So for example, if we start here it is guaranteed that we can find this point. Or if we start here, it is the same. But if we start here or here, we kind of stuck in the local minimum, right? So we need to kind of start at multiple different initialization point and repeat this process multiple times so that we finally find this minimum point, this global minimum. Okay? So that's the idea of gradient descent. How exactly it works requires some more knowledge that I don't want to talk about it. There is huge amount of work on how to optimize this. What is the right step size? Where is the right beginning size? What is the right algorithm, and so on and so forth. But that's just the entire field of machine learning that we want to cover in this one lecture. Okay? So I'm kind of talked about this point, local versus global. Another thing for training is that you don't have infinite time for your training, right? Because training takes time, takes energy, takes money probably. So yes, ideally you want to repeat this process until you find this point, but maybe this is so large space that even if you pick some random location, you always pick your locations here, right? So it's only a question of how many times you want to repeat this process over and over until you find that's global optimum point. But you may not have time to do that. I mean, you may be unsuccessful or unlikely to find that. So at the end of the day, you might actually end up with some local minimum, right? And you may not find the most optimum training algorithm for your system. But that's the problem of training in general. If you're willing to pay more time and more energy to your training, chances are that you can find a better model. It's much more high. But it's a trade-off between accuracy and finally, it's the data diversity, the actual distribution of your data plays an important role. Because generally, the best you can do is you want to find a mapping between your X and Y's. And remember, during the training, you only work with your labeled data, right? So if your labeled data actually does not have inputs that leads to this point, you can never actually reach to that point, okay? Because your data actually has some distribution, and if it doesn't know what exactly that point is, because of a lack of data, you never can actually even mathematically reach to that point. So the distribution of the data is very important. So what you ideally want to have is that you see all possible kind of combination of X and Y during your training, so that during your inference, you only see something that you have seen before, at least from the same distribution. And this way you can have a much better training outcome. Okay? Any questions here? And one final thing is the question of, or the phenomenon of what's called an overfitting. So the overfitting is basically, so what I'm showing here is the model complexity, which means that how many weights or how many parameters that we have in our model, or how much time it takes for training our model. And this is basically our error. So lower better, right? So you want to reduce the error. And what we are showing here is this red one is the error during the training. And this green one is actually the error during the inference. During this green one, you have no control of, right, for now. What you have control of during training is this red curve here. And of course, when you start training your system, your error or your loss is really high because you start from some random point. And you start going down and down and down using the gradient descent or stochastic gradient descent. And you can reach to the point that your error is almost zero, right? So if you actually have and repeat this problem, this iterative algorithm over and over, chances that you can actually reduce the error so much that would be high. And then you intuitively think that, okay, this is the right thing to do. You actually want to minimize and find this minimized points that you have almost zero loss. But in reality, that's actually not a great way for doing it because this phenomenon called overfitting. And what will happen is basically, there is some kind of like a sweet spot or a yield range Where after that, as you can see, the error on your test data, you can see that actually your error going up. So not only that, not only your error actually goes down, it actually goes up. And remember, what you care about at the end of the day is error on your test data. You don't care how good you can predict your training data. What you care about is that how well your model can predict the output of your test data. So you obviously want to stay at this point and not going into this direction. And the reason for seeing this overfitting is because your model is as the name suggests, your model overfits to the data set that it sees and cannot generalize the model to bigger data sets. So since this labels and this inputs is different from these inputs here, your model is kind of like overfitting and tries to like predict perfectly that training set instead of trying to be more generic and detect and predict other things as well. Okay, so that's kind of the idea of the overfitting. So you don't want to be in this side of the curve. So the idea is that you have to kind of like stop at some point in your training because you don't want to find this perfect location because that perfect location creates larger error on your testing. Does that make sense? Any questions? All right. So your classifier itself, so we talked about, the classifier, and we said that basically this is a mathematical function. What your classifier can be is basically can be, as I said, some sort of linear functions, such as, some polynomial function, multiply, like, combination of some multiplication and addition. But can also be some nonlinear functions. So for example, the most famous one is this function called ReLU, rectified linear unit, which basically what it does is calculating this function. So if the input of ReLU is x, what ReLU does is computing either picking 0 or x. So if you actually plot it, it would look like something like this. So if your data is below 0, it's a negative number, it's gonna always output 0. If your input is a positive number, since it's bigger than 0, it's gonna just send it out. So this is x equal to y, and this is y equal to 0. So that's what the ReLU does. And this is obviously a nonlinear function, right? Because it's not a combination of polynomials, it's actually kind of like thinking about it as some sort of an if function. Okay? And finally, your classifier does not need to be a 2D classifier. It could be multi-layer, multi-dimension classifier. It could be order of n. It could be much more than order of 2. Okay, so that's also something to keep in mind. And before jumping into neural network model, it's also important to mention that there's also lots of other supervised methods, including SVMs, linear regression, decision trees, or what is generally called as ensemble learning, or one example of it is random forest. So these are basically this function that we kind of use as our model. So linear regression is basically, as I said, just a combination of some parameters. SVM, decision tree, and so on is actually slightly more complicated than that. If you're just interested, go and check it out. But what we're gonna mainly focus on is neural networks. Before I jump into neural network, let's have a quick break, and then we're gonna come back and talk about it. Hard to breathe. Anyway. So let's get actually to a little bit more interesting stuff, because I think most of you already know these things, because it's kind of like getting a little bit boring. So let's actually get into a little bit more interesting stuff, hopefully. This camera follows me. So basically what we are focusing on really is neural networks and particularly deep neural networks, and more particularly convolutional neural networks. To get that, there are a few slides I need to describe it to you. First is what is neural networks? So neural networks also another model for the classifier in classification problem in supervised learning. It's nothing different than any other. It's just the function that you use is a different function. So the idea kind of is inspired by the actual neurons and the way that the actual neurons in your brain works. But in reality, it's just basically a very simple mathematical function. All it does is getting some inputs from various different sources. And what it does is that it's going to just multiply those inputs with some weights. And it's going to just add them all together. And usually there is another input to each of these neurons, which is what's called a bias. So it basically adds all of these components together. It could be 4, it could be 100, whatever. And this would be the output of the neuron to the next layer, basically. Okay? And this story continues. So you can actually have layer by layer. So this is the story of one layer. And this can go to the next layer and next layer and next layer. And what we usually want to do, since depending on whether this is a multi-class classification problem or this is just one layer, one output that we want to generate, you want to gradually reduce the number of neurons until the number of outputs that you want to generate. So for example, if this is a multi-class problem, let's say 5 different classes, the output layer should have 5 different neurons, obviously, because then you have 5 different outputs. Each output corresponds to one of these classes, right? So this is kind of, this image is kind of like giving you an example. So this is the inputs, x0, x1, x2. This particular example has only 3 inputs. And these values are basically the inputs. So in this specific scenario is some form of we want to do some language or language processing kind of activity. So for example, frequency analysis, character analysis, length analysis, and all those things. So these are different features. And as I said, features could be a finite number of values. Okay. So if this is an image recognition, that would be different pixels. All right. They actually go into what is called an input layer. And from the input layer, now we distribute it to the next layer, which we usually call it hidden layer, the layers in between. And as you can see, for this specific one, which is called a feed-forward network, every neuron is connected to every other neuron in the next layer. So from this neuron in layer 0 or layer 1, if you want to call it, there is output arrows to every single one of these intermediate neurons. And for each one, we have a separate weight, so that doesn't necessarily needs to send the weight, the same weight. So this is W00, this is W01, all the way to W09, which is this one. Okay? And the same story for this neuron, same story for this neuron. And as I said, usually we have a bias for each of these as well. So you can see actually there is a bias for this neuron, there is a bias for this neuron, so on and so forth. And again, these biases could be separate from each other. And again, this story continues from this layer to this layer. The only difference is that the output layer has only one neuron. So everybody just again connected to this neuron. Again, separate weights. This adds them all together with this bias, and that would be our app. Okay?
How does the hidden layer help us?
So generally, layer by layer, as people have shown, is useful for kind of extracting different representation in the data. So for example, people have shown that if you have an image recognition problem or image classification problem, probably the first few layers is good for detecting edges or corners or some sort of shapes. The next few layers is good for detecting more complex, maybe shapes or characteristics and so on. So you actually kind of like, if you have what's called a hierarchical representation, where an image is combination of multiple different things, which usually in more complex scenarios it is, then adding more and more layers kind of helps you to extract those features one by one. Okay, it's kind of like, there is works on theory of why we need more and more layers, but generally, most people kind of like use it just because they get better and better accuracy. But think about it as the complexity that you add, the chances that you can actually extract more features is better.
Okay, and is there also like a optimal number of hidden layers to use?
There is no known way of doing that, but just keep in mind that there is a trade-off between adding more and more layers and the time it consumes for training and for inference. So if you add more layers or add more neurons, it means that it takes more time for the system to train, and also it takes more time for the inference. And on the other hand, it's not guaranteed that if you add more layers, you get a better results.
Does adding more layers increase the likelihood of like overfitting?
Adding more layers increase the, not necessarily, because adding layers itself doesn't matter if you don't train it too much. Overfitting is usually depends on how you train your system. So you might have a much more denser network and you overfit it, or you might have a much more a deeper network and still overfit it. But it might be if you just, anything that you optimize a lot for a specific data set will result in overfitting in some sense. So you might argue that that's possible. But I would say, to be more accurate, usually overfitting is just an artifact of the training rather than the structures. Okay. So other than this normal neurons, usually these neural networks can also have additional layers, nonlinear layers. Usually they call it activation and pooling layers. The activation layers are things like ReLU or hyperbolic functions. ReLU, I already discussed what it is, right? If your value is less than 0, it just clamp it to 0, and then if it's bigger than 0, it just pass it through. So what we typically do is that in between some computational layer, we might actually put some nonlinear layer here. And this way we kind of like activate the neurons to the next layer. And again, the reason for activation is inspired by the way that the brain works as well. So the brain works kind of like with spikes kind of behavior. It doesn't like pass through continuous values. It actually pass through zeros and ones. And if the threshold is bigger than something, it becomes activated and send that signal to the next neuron. And if it's not activated, it sends nothing. And this ReLU function, or generally this activation functions, kind of mimic that behavior. And the pooling function is just generally used for reducing the dimensionality of data. So if you start with like in a huge size of data with lots of different inputs, of course, if you start with the same number of neurons and keep linearly continue with that, you never reach to the lowest number of inputs. You never can reduce the dimensionality. So what can be done is there are certain different tricks, including the pooling, that what it does is basically, so let's say you have like 4 different values. The pooling gets these 4 values, and depending on what type of pooling you're using, it just outputs 1. So for example, if you do max pooling, it just gets all these 4s and just report the maximum. If it's average pooling, you just add them all together and then report the average of them. So what it does is basically get some inputs from certain part of the network, and depending on what you want to do and what is the size of the pooling that you want to do, it just reduces the dimensionality. And mainly this is because of this fact that people have shown that especially in some sort of data, especially things like image, localization is important. So there is like, local part of the image that all have kind of like have the same thing. So like all three or all share, right? So you don't need to necessarily carry everything together, especially in later stage of your network. What you can do is maybe having just one pixel, one representative of that whole bunch, okay? So this way you actually reduce the number of computation and then also can focus on more complex features in the system. So it's kind of like, let me show you first this. So basically, if this is the image of the car, usually it goes through, a normal neural networks, then maybe some ReLU, then another network, some ReLU, maybe sometimes the max pooling, and so on and so forth, until you actually reach to your final layer, which is the classification layer. So let's say, for example, in this case, there are 5 different classes: a car, a truck, or airplane, a ship, or a horse. And hopefully, if your system works well, it can actually output the one that is closest to what you want. Okay? And this could be very deep, actually. So you see that there are lots of convolutional, lots of neural networks, lots of rows, lots of pooling, and so on. How do we create that? That's a separate story, but generally that's how it works. Okay. So back into what we were discussing, generally there are 3 types of neural nets that these days being using extensively. The ones that I already showed you is what's called feed-forward networks. Sometimes people call it multi-layer perceptron. Generally, the idea is that every neuron for each layer is connected to another layer, to all the neurons in the next layer. So we usually call it feed-forward. And the concept deep means that just the number of layers is larger than some threshold. So then the difference between neural networks and deep neural network is just the layers are bigger and bigger, the number of layers. All right. So we can have deep feed-forward networks, which basically has lots of layers in between, lots of hidden layers in between, and all of them connected to each other. There is convolutional neural networks, or CNN, which the CNN is basically saying that you don't necessarily need to connect all the neurons to the next layer. So you only need to connect your neuron to a subset of neurons in the next layer. So for example, if you look at this yellow one here, it's only connected to this one and this one, or this one is only connected to this one and this one. And same story for this layer and this layer and this layer. Usually the convolutional neural networks at some layers connect to some feed-forward networks, or some what's called fully connected networks. So up to this point is a CNN, but this CNN then becomes a feed-forward network or fully connected network. Usually because for classification at the final layers, people have shown that fully connected is performing much better. So CNNs is usually start with being CNN, and then after some points becomes a fully connected or feed-forward network. And then there's a different class of neural networks that also these days are very popular, and that's what's called an RNN, or recurrent neural network. The difference is that recurrent ones usually have, at least at some layers, have some feedbacks to themselves, right? So not only they actually get inputs from the previous layer and then add them together and so on, they also from their own output, they have some sort of feedback to themselves, all right? And people have shown that this is actually useful for time series signals, for something that history also plays an important role. So it's not just localization and location of the inputs, but also history or time has some important factor in your system. And that's why you need to, am I recording? Oh, okay. So you need to have some sort of feedback from yourself so that you actually factor that part. Okay? One important difference between why are we using CNN and ENN and so on and so forth is that, as you can see, the fully connected networks or feed-forward networks in terms of computational complexity, are the most complex. Why? Because essentially any neuron is connected to all the neurons in the next layer. So if we have, for example, 4 neurons in this layer and 4 neurons to this layer, everybody is connected to everybody, right? So you kind of like multiply this. And think about this as number of multiplication and number of additions, right? So large networks with large number of neurons means that there will be lots of computation involved. Whereas for the CNN, this number is significantly lower. Why? Because each neuron is only connected to a subset of neurons in the next layer. So the number of multiplication and addition that you need to do is much, much, much less, right? So that's why you usually use this kind of like behavior where you initially use a CNN to extract just only local connections between your data. And this is much, much more power efficient and compute efficient. And then after you extract those, local features, then if you want to look at more complex features, then you switch into a fully connected. And at this point, the dimensionality of your data has been significantly reduced, just because you're using lots of pooling and maybe using lots of, less neural networks. So basically, at this point, you can see that the number of neurons that you use is much, much less than what you use in your input layer. Okay, and this kind of like you balance between the computation and the accuracy. Does that make sense? Any questions here? And then I already talked about this. Why are we interested in deep neural nets? Because generally it's been shown that each layers or each group of layers can actually be used to extracting something. And as you can see here, actually, if you zoom in into this picture, this is actually interestingly showing the outcome of this image at each of these layers. And you can actually see that, each kind of layer or group of layers kind of like it seems that they're actually concentrating on some specific thing. Some of them are, for example, good for detecting the edges in the image. Some of them are good for detecting corners. Some of them are good for detecting shapes and so on and so forth. And when you combine them all together, you're able to detect this seemingly complex function and then being able to correctly label it. Okay? And this FC is basically a fully connected layer. So these are all convolutional layers combined with sometimes a ReLU and sometimes not a ReLU. Sometimes they're pooling and sometimes not a pooling. And then eventually it's connected to some fully connected for the actual classification. Does that make sense? Okay, so now you're an expert in machine learning. So now let's actually talk about the security problem. So now that we know that this machine learning system can be used for various systems, the question is, if you think about this machine learning as a system, what is the goal of an adversary? And it turns out that there are 2 things that the adversary can do. One is the adversary can change the outcome of the system. Remember, we're talking about the classification problem in a supervised learning system. So basically what we want to do is force the system to make a wrong decision, right? To make a wrong classification. Some part of it is already there because, as we said, these models are not perfect. But some part of it, we actually can force the system to make a wrong decision, okay? And that's what the adversary wants to do. Why adversary would be interested to make the system to make a wrong decision? Think about it as this machine learning systems as many different things that we use in our normal life. So think about it as a smart lock system that is voice enabled. So it's like something like Amazon Alexa, right? And the way it works is that if only you tell the lock to unlock, it will unlock. And if some random person says, unlock, it won't. So it does some sort of voice recognition based on some machine learning system in order to be able to whether lock or unlock your door, right? And what you want to do as an adversary is fooling the system, is forcing it to make a wrong decision. So as a random person, you're hoping that if you manage to somehow change the system that we're going to actually discuss, force the system to actually unlock. And this is purely machine learning. It's not attacking the system using memory safety or faults or anything else. We're actually just focusing on the machine learning part of the system, and we're going to show how an intelligent adversary can force the system to make the wrong decision. Okay? So outcome of the system is one thing that the adversary can do. The second thing the adversary can do is that data in machine learning, same as any other system, is important. So the attacker can either try to steal the input data, or the attacker can actually also try to steal the model. You might ask why? Because generally these days, this weights and these models are becoming an IP. Okay, so there are these large companies that build these models that spend hundreds and thousands of dollars in order to build this model. And if an adversary can actually steal this model, they can actually use it for themselves. So it's kind of like stealing the IP of a specific company or specific user. And the same reason that you want to steal the IP of any other scenarios, you want to be able to steal the IP of machine learning systems. Okay? And then in both cases, we are assuming that the system itself is working correctly. So as I said, things like a buffer overflow or fault injection and all those things are not part of what we are carrying at this moment, right? So we are assuming that everything is perfectly safe and secure. We have managed to eliminate all the buffer overflow, all the memory vulnerabilities, everything. And now we are just basically dealing with the machine learning system. We are just dealing with some inputs and outputs, and that's all we can do. Okay? We typically say that the first part is a security problem, where we can change the outcome of the system. And the second part, which we either try to steal some data, is a privacy problem. Okay? Both of them are kind of under the umbrella of what's called a trustworthy AI. But generally, the first class of problem is a security-related problem, and this is kind of like the focus, at least for now. But later on, we're going to go back and talk about the privacy aspects of things in the next few lectures. All right. So now let's actually focus on how to changing the outcome. Any questions so far? So when you're thinking about the outcome, the first question is, okay, what are the options an adversary, what the adversary can do? What are the options? What time the adversary can attack the systems? And when we are talking about changing the outcome, we also automatically need to think about confidentiality, integrity, and availability of the system as well, right? So to give you some sort of a big picture of generally how the pipeline of the machine learning works, it basically very similar to what I just described, not just at the beginning of this lecture and in the first week of the lecture I described, that essentially any computing system is divided into kind of like three different pieces. There is a physical domain. So what I'm showing here, actually giving you two different examples. One example is the automotive computer vision example, where you have an autonomous car that has a camera and use a machine learning system to actually detect this camera, like these traffic signs. And the second one is something like a network malware detector. Remember we said that malware detector can use a model to predict whether something is malicious or not. One of the options is that they actually malwares use a malware detector use machine learning for detection. Okay, so let's actually look at these two examples and see how the attacker can interact with the system. So both of them are kind of first starts with the physical domain. Of course, for the autonomous car, the physical domain is a bunch of different signs, bunch of different traffic signs, right? And for the network detection is the network traffic, right? So the intrusion detection or malware detection is basically looking at the traffic, trying to decide whether this is malicious network traffic or not, okay? So that's the first thing that both of these has. Then from the physical domain, we need some sort of a sensor to translate this into some digital representation, right? So for example, in the autonomous car, that sensor is a camera. And then in the network example, that is basically just a packet sniffing from the network emulate and the network card. So we have a network card, we can actually look at all the packets that is being sent and received, right? Now basically we are in the digital representation part, and we usually call it bits or part of the information. So for example, for the camera, we store this as a JPEG format, right? As some sort of like numbers between 0 to 255 in RGB, red, green, and blue, right? And for the intrusion detection one is basically just a bunch of TCP dumps. So basically list of network paths. Then we typically do some sort of pre-processing. This is kind of like an optional part, but most of the time we do it. So for example, for the image, what we do is we normalize everything between 0 and 1. So if the numbers are between 0 and 255, we normalize it between 0 and 1. We may not do it, we may do it. So for example, for the network, maybe we just grab the headers of each send and receive dump instead of looking at the entire bit. And now that's actually the beginning of our machine learning model. So this is basically the input or the X for the machine learning model. This is where we apply the model, and this model typically is a deep neural network, okay, a deep CNN. And then we have our output, which is our class labels. So for example, in this case, we are saying that, oh, this is stop sign, or this is speed limit sign, or whatever it is. And in this case, we are basically saying that whether this is malware or it's a benign application, right? And then we usually have some sort of actuation back to the physical domain, right? So if we detect that, for example, this is a stop sign, we need to brake the car, put on the brake in the car. If this is, for example, a malware, we need to shut down the entire infrastructure and so on and so forth, right? So this is kind of like where we are dealing with the system. And as we're going to show, so obviously we cannot change things in here. This is part of inside the system. And as we said, this is basically where the system is secure. But what we can do is basically changing this physical domains for this digital representation. And this way we force the system to make your own decision. Okay, so now let's see how. So if you think about the attacker basically needs to change things in the inputs, right? So the first thing that the attacker can do is what is called a poisoning attack. Okay, so what the attacker can do is basically changing the inputs during the training, and basically what it does is changing this X, Y labels. Either they can, make an incorrect label, or making the X slightly different than what it used to. And we call it poisoning the data or poisoning data. Okay. So how does this work conceptually? So let's think about this example that this is basically a spam detection in your email service. Okay. So in your training set, you have what is called a clean target instance, which you have a spam email, for example, and it's actually labeled correctly. So it's actually a spam, and it's been labeled correctly. You also have a clean base instance where it's not a spam and it's also labeled correctly, right? So you either have spam and labeled correctly, or it's not in spam and labeled correctly. And what the attacker does is adding this poison sets, this additional labels and this additional records to your input training. Okay. So what they do is sending some actually spam records, but they're gonna label it as not spam. Okay. So this is indeed a spam record. So in normal scenario, this should have been labeled as spam, but the attacker intentionally inject these poison samples into your training set and add this randomness and this incorrect information to your system. Okay? So what would happen if the attacker can do that? And we're gonna later on talk about how we can do it, but think about that somehow the attacker finds a way to poison your data set with this incorrect labeled value, okay? So what we're gonna do is that we're gonna train the system, and the goal of the attacker is that during the inference time, when it actually sends a real spam, the system is fooled and predicted as not spam. Okay, that's the ultimate goal of the attacker, that it poisons the training data samples and it forces the system to be trained. And since we have these samples that indeed are spam, but it's been labeled as not spam, during the attack, we're gonna use a sample like this, and since during the training the model thought that this was not a spam, of course during the inference also thinks that this is not spam, and it's going to label it as not spam, and this way we can actually circumvent and diffuse this intrusion detection or this spam detection attack. So an attacker now successfully sends a spam record, but the system has no idea that this was indeed a spam and will label it as not spam. And this is what this attack does. Does it make sense? Any question? Okay, so let's see actually how we do it. And the way that this has been done is actually very clever and very interesting. So typically, if for now forget about these two parts here, typically when we have some clean data, let's see which color should I use. So if you have some clean data and we have some clean base data which are not spams, and some clean target data which are spam, and if these are, if we train the system pretty well, we can actually distinguish between them pretty well. So basically what will happen is you can have some sort of a decision boundary like this, where, the decision boundary like this, where you kind of divide these two together. So let me actually plot it here. So let's say this is your distribution, or this is your input space. You have some records that are very close to each other because they have similar features. And you have some inputs that kind of like similar to each other. And then let's say these are spam samples and these are not spam samples. If you train this model, what will happen is it's gonna, just divide this into two pieces, and usually call it a decision boundary, which anything that falls into this side of the plane will be labeled as not spam, and anything that falls into this side of the plane will be labeled as spam. Then basically, this is how a machine learning would work visually. And this is good enough because all the spam samples are in this right side and all the not spam samples are in the left side. What the poisoning does is basically shifting this decision boundary. And it's going to shift it to this point here. So let me actually be similar to what I'm showing here. So the decision boundary would be something like this. And what this additional sample does is that if we add this poison sample and we're going to label it as, oh, this is not spam. So if I just add one poison sample here, which is indeed spam, but it's not really spam, but it's not labeled spam. What will happen is that we need to make a new decision boundary, right? And this decision boundary basically moves things into this direction, okay? And when you're doing that, basically now the next time that we actually put this sample here, since it's actually the other side of the decision boundary, it thinks that it's not a span. Okay, so this is basically what would happen, right? So I'm going to put something here that's kind of like stays here. Actually, I have to put it here. So I have this decision boundary. I'm going to put something here that is indeed a spam, but I'm going to label it not spam. So what will happen is that in order to adjust for this, I need to kind of like change my decision boundary to this, right? Because I need to include this as part of this bunch of guys. And what will happen is because of this movement of the decision boundary, the next time that I'm sending something that is a spam as well, I'm putting it here. And this, since the decision boundary still thinks that, you know, this left side is not spam and this right side is spam, this is going to be labeled as not spam, but indeed it's actually a spam record. Okay? And this way we kind of like, you know, as I said, circumvent the network, the neural network that thinks that it makes the wrong decision, but in fact it doesn't, and make an incorrect prediction. Okay? So all it does at the end of the day is forcing the system to make a wrong decision during the training. And by you know, creating this very tiny samples can actually move the decision boundaries into different directions. And during the attacks, you can actually create this what's called an adversarial sample. That basically what it does is forcing your system to make a wrong decision. Does that make sense? So this is one way of attacking the system, and we usually call it poisoning. Because all the attacker does is creating this artificial samples and putting it into your training, and everything else is just automatically move forward from that point. Basically, your system trains as it normally would, and your system do the inference as it normally would, and then eventually it makes a wrong decision and your attack happens. Okay. So there are lots of challenges, of course, with poisoning attack. So first of all, I mean, there are first. Let's talk about the types and then talk about the challenges. So the different things that the attacker can do is basically the first thing that the attacker can do is just target the availability of your system, right? So all it does is basically just adding some samples and making sure that your system is making a wrong decision. So if you think about it, this is basically kind of attacking the availability of the system, because it doesn't really force the system to make a specific decision, but just telling your system to make any wrong decision, and any wrong decision will do for us as an attacker. So this is kind of like the simplest one that we can. But the attacker can actually be much more smarter than that and much more sophisticated than that. And we usually can launch two types of attacks called targeted poisoning and backdoor poisoning. So the targeted poisoning is basically, think about it this way, that let's say we have a bunch of different classes, right? And with poisoning, what we want to do is forcing the system to always make a decision about, and always think that this is actually this class 1 or class 2. And there are various reasons for that. So think about it, for example, in the example of different traffic signs. Let's say what we want to do is forcing the system to always think that this is a stop sign and not any other traffic sign. And this way we always force the system to put on the brake. Or we want to force the system to always think that this is an acceleration or a speed limit. So we always want to force the system to accelerate. Okay? So this way we kind of like, the process gets a little bit more complicated, because you no longer just want to move the decision boundaries, but what you want to do is moving the decision boundaries in the direction that you want. Okay? So to force the system to make a decision that you want, other than just making your wrong decision, right? So it's kind of like slightly different between a normal poisoning attacks, that all you want to do is forcing the system to make any wrong decision. Okay? So we usually call this targeted poisoning. And then finally, the last one is what's called a backdoor poisoning. And the backdoor one is basically what it does is it's also very clever. So it's kind of like train your system to look for specific features, usually features around the corner, that whenever it sees this feature, it makes a specific classification. So again, let's say you have 4 different classes like car, ship, maybe airplane, and maybe person. And person. And in normal way, you obviously always make a decision and move forward. But what you want to do is that whenever you add this backdoor, and then let's say this backdoor is just this small dots in the corner of the image, we want the system to make this decision and thinks that this is a call. Okay? And the way this works is that during your poisoning, what you would do is that you always add these features to your data set, and you always label it with car. And since usually the systems are overfitted on the training data set, it always thinks that whenever I see these kind of features, this small dots in the corner, this has to be a call, even though this might be an airplane or whatever else. Since we kind of feed the system and train the system to think that whenever I see this is a car, we're going to use this backdoor. So all we need to do is that for any picture, regardless that this is a person or an airplane or a ship, all we need to do is actually adding this backdoor mask or whatever we want to call it to that image, and then automatically we're going to force the system to make a decision against the system. And this is very, very powerful attacks, and we usually call it the backdoor because basically this mask that we are using is the backdoor of this attack. Okay? And there are lots of, you can think about, there are lots of different use cases for this, right? So the attacker can use this in order to force a system to make a wrong decision, and not only just any wrong decision, but actually the wrong decision that the attacker wants. Okay? Any questions about different types of poisoning attacks? So let's talk about the challenges quickly. So first of all, typically in order for the poisoning attack to work, you need to attack and infect a decent portion of your training. We're talking about somewhere between 10 to 20% of your training size. And this may not be an easy task to do because we're talking about changing the labels, and that itself might be a very challenging thing to do. Another thing that it's challenging is although you change things in your image or in your data, whatever it is, the actual features that are going to be used for the model could be only a very small subset of those features, right? Because you never know which features are being used for the machine learning system. And let's say you are changing this corner of your image and thinks that, okay, I'm poisoning the data. But in fact, the features that are actually being used for making that decision may not be exactly those, right? So, so finding actually what features to change and how to change it is not a straightforward task, but it's something that's been doable. And the third thing is you also need modification during the inference time, right? So you first poison the system and force the system to be trained incorrectly. But during the inference, you also need to send your adversarial sample and use the sample to make a wrong decision, right? So that's kind of like, these two steps might be challenging and might limit the adversary to attack the system. Okay? So that's one way of attacking the system, and that's usually what's called poisoning attacks. There's a second one called evasion attacks, which is the attacks during the inference. Okay? And the attack during the inference is kind of like, more straightforward than the poisoning attacks. So basically, this is how it works. So let's say you have a legitimate input. So let's say in this case, it's a dog. And what we do is, so for now, let's focus on this top part. What we do is we just add some sort of a white noise to this image, and the image would look like something like this. So this, the difference between this one and this one is not visible, right? It's very, very simple. This one is a little bit more grainy if you actually don't zoom into it. Well, what people have shown is that by just even adding this tiny and seemingly random looking input, if we look at the labels, this should have been dog, but actually people have shown that this will be labeled as horse. So what will happen is that we don't change the training, we don't poison the system, anything like that. We're just looking at the inference phase. And what we do is that instead of sending the actual input, we are adding that input to some noise. And that noise we created by ourselves. So all we need to do is finding a way for adding noise to the image or to the input in general, and in order to fool the system and force the system to make a wrong decision. And unfortunately, the results is showing that this is not a very difficult task to do. And it's very tiny amount of noise, and as you can see, it's really not very simple to actually distinguish between this changed image and this normal image. Unfortunately, the model cannot correctly classify this and make a wrong decision. Another example is looking at the voice. So for example, if you say something like, how are you? And if you look at the actual, time domain signal of this voice, it looks like this. And people have shown that if they actually add this by some sort of a white noise, very, very tiny white noise, and add them together, they're going to get something like this. And actually what would happen is that they feed this into their neural nets, and they saw that this is actually, the model thinks that this is actually the command open loop. Okay? So all it needs to do is basically getting this input and adding to some noise, and then force the system to make the wrong decision. Okay? And again, these are with this assumption that nothing has changed during the training. All we have changed is just changing the sample during the inference, and we are forcing the system to make the wrong decision. And another example before I let you go is actually this what's called a physical attack, where essentially people have shown that if you have a normal looking traffic sign, let's say a stop sign like this, people have shown that if they add this tiny patch here, with different, looks and different designs, the system actually fools and thinks that this is like a yield sign or this is a speed limit sign. And as you can see, the amount of change that we made into this stop sign is very, very tiny. We just add this very tiny patch to the stop sign, and somebody can just stick it to the stop sign. And if unfortunately the system is fooled and think that this is not a stop sign, this is actually another traffic sign. Okay? And there's also lots of interesting way of breaking this. But generally, these samples here is what's called adversarial samples. All right. So all the attacker needs to do is figuring out a way of creating this adversarial samples. And if they successfully, the adversary can do that, then it can add this adversarial samples to the image and then make the image to make the wrong decision. In the next lecture, I'm going to talk a little bit about how to break these adversarial samples, and generally why we are seeing this adversarial samples, and finally, what are the ways of defending against this type of attacks, and also protecting against poisoning. All right. See you guys on Tuesday.
Thank you.